Welcome, my friends. This is William M. Briggs, and I'm going to do a brief discussion. I always end up rushing and saying too many things, I think, but I'm going to limit my comments on Newcomb's paradox and a new solution to it. Let me give you the setup, and then we'll discuss its supposed difficulties. And then I'm going to add a twist. There's been many twists and so forth, but I'm going to add a new twist and give you a general solution for when uncertainty is introduced. Now, it's a very simple setup. You got some presumably rich eccentric who we'll call a guesser, who might be an oracle, I guess some people say, or just another entity. Somebody playing this game, he's going to fill two boxes. A, which will always have $1,000, no matter what, and B, which will have $1 million or nothing. And the rules are very simple of this game, very simple for you anyway. You could take just B, you could just take this box, or you could take A and B. You can't take just A for whatever reason. I don't know why you would, but you could. You could not do that in this game. Now, if the guesser, this is the whole point of the paradox right here. If the guesser guesses you'll take just B, he fills it with $1 million. All right, if the guesser guesses you'll take B and B alone, he fills it with $1 million. If the guesser guesses you'll try to get the maximum amount of money you could squeeze out of this, which is $1 million and $1,000, he'll leave B empty. So if he guesses accurately that you'll try to take both, he leaves this empty and you'll come away with only $1,000. That's it. Now, why is this a paradox? It's a paradox. A paradox is a way that a challenge in your thinking and your assumptions and so forth to maybe lay bare premises in your arguments that you didn't know that you were relying on. In other words, implicit premises and so forth that lead you down a certain path that you weren't aware that you were even making. So let's look at this one right here. So we have this guesser, and you're playing the game with him, and you and he are sitting apart, and he's looking at you, sizing you up, and looking for your tells, for instance, or whatever it is that the guesser is using to know all about you. And he makes his guess, and he sticks the money in, or he doesn't, and then you make your subsequent choice. Why this seems to be a paradox is that the guesser could do this a week ago. He, a week ago, could have discerned what you were going to do. You're walking up to the boxes, and this was a week ago after having been informed of the rules, and you haven't even made up your mind what you're going to do. You yourself don't know. You might even think you're going to flip a coin when you get there. You're not quite sure what's going to happen. But the guesser, in all of these paradox, or all of the explanations for it, is supposed to be very good, nearly perfect. It's the quantification by what people mean by nearly perfect or very good or all that kind of stuff is never given. That's what we're going to do. We're going to give it. I'm going to show you what happens when we can quantify it. But meanwhile, it seems like a paradox because this guy is going to be able to guess what you're going to do. And if he guesses you're going to be greedy, he's going to leave box B empty. And if he guesses you're going to be somewhat nicer to his accounts, you're only going to take box B and come away with $1 million. That seems like a paradox because how could this guy be able to know what you're going to do this far in advance? Well, so what? I mean, it's not so much of a paradox. and the idea is, well, if this guy is so good, at guessing what you're going to do, how could you possibly have free will? Some argue. Because this guy is going to know exactly what you're going to do, and so if he could guess exactly what you're going to do, then you don't possibly have free will. Well, that doesn't follow. You know tomorrow morning you're going to bake some cookies, or your wife is, and she's going to leave them out and leave them unattended. And at that point, you know your child is going to take one of those cookies. This does not obviate the free will of your child. The child has still made a choice to take that cookie, even if you predicted accurately what the child is going to do. So free will hasn't been removed simply because there's a very good guesser. And of course, the infinite pound gorilla in the room is God in omniscience. With omniscience, God is able to know everything. including what you're going to do, no matter what you do. But this does not, of course, take away your free will. It merely means that God knows what's going to happen. It doesn't mean that you haven't made a choice. And theologically speaking, anyway, William Lane Craig has a book on this. I have it in the article, which I'm going to link below. You could find a link to his article, rather the book on this subject, if you're interested in that particular thrust. But I don't think it has much weight anyway, because, for instance, in our physical models and so forth, we're going to predict, you can predict right now that the sun's going to come up a week from now in the east, or a month from now, or a year from now, or 10 years from now. You predict the sun will come up in the east. Your accurate prediction, and it's going to be accurate, has nothing to do with the sun being caused to come up in the east. So just because you're actually making good predictions does not mean you're causally interacting with whatever it is you're predicting. So you're not removing the forces from the sun, or the powers of the sun in its movement, or the Earth's movement, I should say. You're not doing any of that by your accurate guessing, and neither are you causally interfering with anybody if they make an accurate guess of what you're going to do, including this guesser. Okay, so let's just remember these rules, shall we? You can always either pause or go back. Oh, I have an article on all this. If you're going to be, flummoxed by the blizzard of symbols to come here, not that many. There's going to be an article at my sites, WMBriggs or wmbriggs.substack.com, that I have all of this written up, and you could follow along more carefully if you want to. Okay, so let's think about the times. Let's add some uncertainty to this. Let's add some uncertainty that we know the guesser, or that is to say, we're going to introduce the possibility of the guesser being imperfect. He may not be omniscient. He may make mistakes. So let's ask ourselves, just what is it? How is it that the box B gets $1 million in it? That's the proposition. Box B has a million. That's the proposition. Let's call the guesser. Well, we know these rules here, so I'm going to erase these rules. And if you can't remember, I'll remind us as we get going. Let's call the guesser Y. Just for shorthand, we're going to call X U. And the box, we're going to sort of abuse notation. A and B means either you take A and B, or there's money in them, depending on how we're going to use this situation. So these are, and R, we need R for the rules. R equals the rules, which I already gave us. Okay. So now, when does B get $1 million in it? B gets $1 million when the guesser guesses B, and you take A and B. That's a possibility. If the guesser is imperfect, he could guess you're going to take B, and still he'll stick $1 million in the box B, but you're actually going to take A and B. Or you could, the guesser will guess you're going to take B, and you actually take B. Those are the only two possibilities at which there'll be $1 million in box B. Now, given our rules, we can calculate the probability of this. Simple. It's just probability of Y equaling B and X equaling A plus B, and so these are that is to say, we could separate these two in the probability, because this one is not influential on this. Knowing this tells you nothing about this. Knowing this tells you nothing about this. So we can separate these in the probability, and this is going to equal, that is to say, plus the probability of Y equals B and X equals B given R. And we have to have it given R because R is our rules. This is what tells us what's going on here. And this is everything we know. This is everything we know about the guesser, about you. Everything that we know is going to be in this R here. This is our background information and so forth. Well, this is very simple. We could just separate this out. This is probability of Y equals B, given that you've chosen A plus B, and the rules are, times the probability of you picking A plus B, given R, plus the probability of Y equaling B, given that you do take B, and times the probability of X, given you pick B, and the rules. There's no problem with this being a probability. Some people, this is where why people must have misrecognized the idea that this can be quantified. This is the probability that you take R. Probability is not a cause. Probability is just a matter of our minds. That's what we've been doing in our class. Probability is epistemological. Probability is only based on the information that we have. And so whether or not you take A or B, you could even flip a coin if it's part of the information you stick in R, but it's whatever you decide. So that has that probability. So we can introduce these here. This could be, what notation did I use? I used the notation 1 minus probability of A plus B for this. And I'm going to use the probability of Q for this. This is 1 minus the probability he guesses correctly. This is, again, this is the probability that he guesses incorrectly given you've made the choice A plus B. And this is the guesser guessing that you're only taking B. And I'm going to make the correct probability of his guessing PA plus B. And we just simply carry this through, and I'll call this the probability of B times 1 minus Q. You could only take A or B according to the rules. You can't, probability is conditional on the information you assume. You can't say, well, I'm just going to take A. That's not part of the rules. Probability is not inherent in things, it's inherent in the logical structures that we set up. And the logical structure we set up, given the rules that we have, is just this. Now, let, for instance, the probability of A plus B equal the probability of B. This is the probability he guesses correctly that you'll take B. These probabilities don't need to be the same. This is the probability he guesses correctly when you're going to take A plus B. Because it's 1 minus the probability he's going to guess B. He guessed B when you say you're going to pick A and B. And so probability of A plus B is the probability he guesses correctly when you take X plus B. If you don't follow that, pause and consider. In other words, we have, given that this is, we are assuming you actually have decided and you are picking A plus B, this is the probability the guesser guesses B. In other words, the probability he's wrong. And I'm going to call that 1 minus the probability he guesses correctly. All right, there's no harm in doing that. So here's our two probabilities, the probability of guessing that you're going to take A plus B when you take A plus B, and the probability that he guesses B when you're going to take B. If we let these both equal 1, in other words, we're back to the original paradox. What happens here? This probability that B has a million, the probability that B has a million is 1 minus 1 is, of course, 0. 0 times Q is 0. I won't even write that up. Well, okay, I'll write it up. Some people who like math. And this is going to be 1, and this is going to be 1 minus Q. So the probability that B has a million, when the guesser is perfect, is 1 minus Q. And what is Q? Q is the probability that you choose A plus B. If you choose A plus B, Q is 1. If you choose A plus B, Q is 1, because that's, you have chosen A plus B. So the probability you have chosen A plus B is 1. And that 1 minus 1 equals 0. And the probability that B has a million is 0, because the guy has guessed correctly. You're going to try to get both boxes, and so that works. So now, what box should you take if the guy has error, if he's not so good at guessing? Is there a better chance that you can get not just the million, but the million and 1,000, or even 1,000 or nothing, because maybe this guy is going to make a mistake in some way? So let's look at that. It's very simple. I think I'll put it, I'll just erase this up here. I'll leave all these down here. I want to leave the equation up here. It's very simple, and it's when all we have to do is see that we would pick A plus B when 1 minus the probability of A plus B is greater than the probability of P plus, the PB, that he's going to guess correctly that you've taken B. The only time you could pick A and B, else pick B. Else you would just pick B. So if they're both 1, this is 1 minus 1, that's 0. 0 is never going to be greater than this, no matter what this value is, because that has to be a number between 0 and 1. So if he's perfect at guessing that you're going to take A and B when you do in fact take A and B, it doesn't matter what his guessing is about B at all. You are, you could only maximize, you would not be able to pick A plus B. You would not gain anything by picking A plus B. All right, that should be simple enough. The only slight twist to this, kind of interesting. Why this equation right here? Well, you just want the probability that box B has $1 million. You only have two things. When you pick A and B, why does this equation come about? When you pick A and B, the probability of Q is 1, right? And I hope you follow that. So when you pick A and B, you can only do one or two things. You can pick A and B, or even if you flip a coin, and that coin is, information about the coin is in this R business right here. Even if you pick this coin and flip the coin to decide what you're going to do, in the end, the probability that you've picked A and B is the choice that you have made. So the choices you have made is the probability of A and B would be 1 if you have picked A and B. That's what this equation stands for, if you're following all this mumble mouth gibberish right here. So Q would equal 1. And 1 minus Q, so we're working with this equation right here. If Q equals 1, well, the 1 minus 1 is 0, so this doesn't matter. And this is 1, and we have 1 minus the probability of A and B, if you've picked A and B. And we want that probability to be bigger than if the probability that you picked B and the guy guesses accurately or inaccurately. If you're going to pick just B, Q would equal 0, because, or 1 minus Q would be, 1 minus Q rather would be the probability of picking just B. And so we'd have only the probability of PB if Q was going to equal 0. In other words, we have picked B, and so the probability of picking A plus B must be 0, and so we have probability of B, and this would be 0, and so we'd only have the probability of B. So we want this probability to be larger than this probability. And so that devolves or creates the rule, pick A plus B if this is bigger than this. So suppose the guy is equally good. This is the only kind of fun about this. If, again, PA plus B equals P of B. These are his correct guessing probabilities. It doesn't matter what they are, but just suppose that they're both less than 1. If that's the case, we could just say that this is going to be, the same equation would be 1 minus P, whatever it is. This is going to equal some P then, would be greater than P. Or take P on both sides, you'd have 2P over here, divide by 1. This means P would have to be less than a half. So the only time you would pick A and B is if these two were equal, or you thought they were equal, given whatever information you have you stuck into R. And if P would be less than a half, if his guessing powers were less than a coin flip for him, although we know a coin flip probability has 1 if we know all the causes, but using the metaphor of a coin flip, if he's a very bad guesser, you would take A and B. If he is a very good guesser, just greater than a half, you would take just B. And so that's the solution, the general solution of Newcomb's paradox right here. If it's a bad guesser, take A and B, and that sort of follows, it's obvious. If you take the extreme case where these equal 0, if you take the extreme case where these equal 0, we'd have 1 minus 0 is 1 times whatever Q is, plus 0 times this, and this would just equal Q. That's the probability of you taking A and B. And you can maximize that probability by taking A and B. That's the idea, because there's no stochasticity in life or in the real world. In the real world, it's all on the information we have, and you're the one who decides what to do. So the best thing you could do then, if he's always going to make a mistake, of course, is take A and B. And he'll think that you're only going to take B. And so he'll load $1 million into B. And so the only time you'd ever want to do this is when he is really bad at making this kind of game. And so, you know, and then concluding he's some kind of eccentric who just likes giving his money away. That's the general solution to Newcomb's paradox right there. They don't have to be equal, but this just gives extra insight into it. It all depends on what information that you happen to have about the guesser. If you think he's better than even at guessing, well, then you'd only take box B. It's probably difficult to keep in mind all of these things, the back and forth, A, B, pick A and B, probability of you. All that stuff is difficult to keep in mind. It's a lot of terms and it's a blizzard of words going back and forth, which is why I have linked below reference to the actual article. I write all this up carefully and slowly so you can read it at your leisure instead of listening to this kind of incoherent mumble jumbo about all these particular things. That's it for now. There's more below. The links will be to wmbriggs.com or wmbriggs.substack.com, WMBRIGGS. And don't forget to sign up to the class. Look at my YouTube channel or any of my websites and so forth, or Twitter, and take the class, which we do all these kind of probability calculations from scratch and learn how the logical way to do probability is the only correct way. That's it for now. Thanks for listening.